Well, before we look at the last couple of theorems in Chapter 3, let's review what we've learned very, very recently. We talked about a closed set, and we defined a closed set. A closed set E, well, a set E is closed if it contains all of its accumulation points. So there's not a point outside of the set that is an accumulation point. A good example would be the open interval from 2 to 3 is not closed. Because, for using the definition, the number 2 and the number 3 are both, neither is an element of this set, but they are both accumulation points of the set. So it turns out that 2, 3 is an open set. So a closed set E, it's closed if it contains all of its accumulation points. An open set A means, by the definition, that the complement of A is closed. That was the definition of an open set. A is open if its complement is closed. Actually, I think that was an if and only if proof. So I could say set E is closed if and only if its complement, R minus E, is open. And then we moved on to compact. That one had a whole different definition. A set is compact if every open cover, let me use a different letter, B. The set B is compact if every open cover contains a finite subcover. So let's review what that means. An open cover of B would simply be any collection of open sets whose union, when you union them all together, contains B. So B would be a subset of the union of those open sets. Now that could be, as we've seen, there could be an uncountable number of open sets, could be countable. But if every collection of open sets, every open cover, if it's a case that you can take a finite number of the sets in here, guaranteed, and have it still cover B, if you can find such a finite subcover from every open cover, then you have a compact set. Now let's give an example, again, similar to one we've already seen, of a set that is not compact. Let's take what I've shaded on the real line is the interval, open interval from 5 to 10. And actually, let's make it closed on one side. This is not a compact set, and I can give an example. We could choose, let's see, if I took the open interval from 4 to 10 minus 1 over n for all n in the natural numbers. Hopefully you can convince yourself that if I take the union of all of these intervals, that union will contain this interval. For example, the very first, when n equals 1, this is 4 to 10 minus 1 over 1 is 9. So we get a good chunk of it right there. This part's covered. Now, if I make n equal 2, we get 4 to 10 minus a half, which is 9 and 1/2. So that one, the next set goes even farther. And the next one would be 4 to 9 minus 1/3, 10 minus 1/3, which would be 9 and 2/3. And then it would go 4 to 9 and 3/4, 9 and 5/6, 9 and 6/7. that union of the infinite number of sets, eventually, that union would cover this entire interval. In other words, this interval from 5 to 10 will be completely contained inside that union. But if you take a finite number of them, a finite number of these intervals, that means at some point you're going to cut it off. And there's none below that. That means you're not quite going to get to 10. This finite union, here's only 3 of them, does not contain the entire interval. Therefore, we took an open cover, which was these sets. This is an infinite number of sets whose union contains this interval. There is no finite number of them that will cover that interval. Therefore, this is not compact. All right, well, the next theorem we're going to look at, second to the last theorem in this section, is called the Heine Borel Theorem, named after 2 mathematicians. Theorem 3.7. H-E-I-N-E, Heine Borel. It's very simply stated. It says that a set, capital E, subset of the real line, is compact if E is closed and bounded. That's it. So this is actually easier, much easier to work with than the definition of a compact set, being that every open cover contains a finite subcover. That defines a compact set. This theorem characterizes them beautifully, since this is real analysis and we're talking about the real line. If you're getting into functional analysis or measure theory, classes you would take beyond this, you'll get to spaces like Hilbert spaces and Banach spaces. You'll learn about those later, not in this class, where a closed ball around a point, which is basically analogous to a closed interval, is not a compact set. But for real analysis, this theorem beautifully characterizes compact sets, closed and bounded. That's all there is to it. So I'm not going to do the proof. It's quite a long proof. You can see it in the textbook, and I encourage you to at least skim over it. But let's take a look at some simple examples. Any finite set could be represented by something like this, where this set contains n elements. N is some fixed natural number. We've got a finite set. That is a compact set. And if we think about it, it's very easy to explain why. If you have an open cover, which means you have the union of a bunch of open sets whose union contains all of these individual points, your finite subcover would contain at the very most one open set for each one of them. So the finite subcover would contain at most n elements, at most n sets. The next one is not really an example. Maybe I'll write it like an example because it's a homework problem you're going to have to do. It says that if A1, A2, up to AN, these are capital A's now, which they're going to be sets, not individual elements. These are just individual real numbers. If A1 through AN are all compact sets, then the union of those sets is a compact set. So I could write it like the union of all of the AI's where I goes from 1 to n. That's the union of these n sets. So it's A1, union A2, union all the way up to AN. This is a compact set. Well, how are you going to prove that? It's really quite easy. Go back in your notes and pull out the mathematical induction proof. And let's say that we have A1, A2, up to AK. Oh, first of all, the base case would be trivial, right? If you have one compact set, it's a compact set. That's the base case. If this collection of sets is only one set, so A1 is a compact set, then the union is compact because you only have one set. You know, it's weird to say, but the union of one set is just the one set. So the base case is trivial. A1, it's a compact set. Now you suppose, for the induction, that if you have K sets, that union of those sets is a compact set. And all you need to do is tack one more set on and prove that the union of all K plus 1 sets is a compact set. But that's fairly straightforward. Let's see. By the induction step, you know this is compact. Right? So essentially, all you are doing is tacking on one more compact set. So the only interesting part of this is proving that two compact sets unioned together are compact. And that's pretty easy. All you have to do is say, well, take a finite, take a cover of all of these sets, an open cover. So it's a collection of open sets whose union covers all of them. Well, for A1 through AK, we know that's a compact set. So there's a finite subcover of the collection of open sets. There's a finite number of them that will cover all of these. That's by the inductive step. Well, this one set is a compact set. There's also a finite number of those in the cover. There's a finite subcover for this one. So if you union together the finite subcover, this one, with this finite subcover, two finite numbers are still finite. So you have found a finite collection that covers the entire set of compact sets. So a simple induction proof, and I believe it's number 36 that you'll be doing. So it shouldn't be too difficult.